What we'll be considering here is the paths or trajectories of different charged particles within magnetic fields. So one of the first things we need to be aware of course, is that if you have a moving charge in a magnetic field, you'll experience a force which is equal to QVB or V perpendicular B, often represented as QVB sine theta. For our purposes, we're going to make sure that the velocity is perpendicular to the magnetic field, so theta equals 90 degrees for our purposes here. All right, so it's going to experience this force. This force, of course, will then be utilized to give you Fc, the centrifugal force, which is mv squared over r. And we know from our work that the result of these two things result in Fb equal Fc, resulting in a circular arc. So that is generally true. When we've got a charged particle entering a magnetic field, we're saying it's going to go through a circular arc. So let's consider this scenario. Let's say we've got a particle that's positive. It enters this magnetic field. We know from our right-hand palm rule that it's going to experience a force upward. And so it will undergo an arc that's probably something along the lines of this. So it will have a sort of anti-clockwise arc. Now, let's say that was a proton. If I go through at the same velocity with the electron, then it's important to recognize that the electron is negative, so it will experience a force downward. And this electron, remember, it'll go through a circular arc, but by solving for it, your radius is going to be mv over qb. Now, in many questions, when we're doing these sort of questions, we assume that the velocity is the same because they've been accelerated the same way. Often we're assuming same velocity and same magnetic field. And then so it's the mass to charge ratio. We'll note that the mass to charge ratio of a proton is much higher because the charge is the same, but proton is a lot heavier. So for an electron, we'll kind of do this. We'll have a much smaller radius. Now that's something we've talked about before, but that might be too simplistic a picture at sometimes. So now let's expand this a little bit more and then talk about what happens now in a different scenario. Now I'll still keep the idea of R equals mv over qb in mind, but let's consider this scenario. So in this scenario, we now have a particle, well, three in fact, we'll consider three different particles. Now, all three of these particles are positive. A proton, a deuteron, and an alpha particle are all positive. So we've got a particle positive particle here. And it is then in an electric field. This electric field, of course, will accelerate this particle. So this particle will then accelerate towards the negative plate. And then it's going to shoot out of this electric field. Now, once it shoots out of this electric field, it will enter a uniform magnetic field, which we will just quickly draw in green. And then once it enters this uniform magnetic field, we know because it's positive that it will experience a force and it will undergo some sort of circular arc, as we described. And this circular arc will have a radius described by R equals mv over qb, as we discussed. Now they're all positive, so they'll all kind of go that way. What we want to do is we want to find the radius of curvature relative to each other in terms of the proton's radius of curvature. So in other words, we understand they'll all go through some sort of circular motion, and we'll just create a new column. So for the radius, and we'll say, okay, the proton has a radius of rp. Well, let's work it out for the proton first. See, we know the radius equals mv over qb. Now the radius of the proton is equal to the mass of the proton times the velocity of the proton all over the charge of the proton times b. But here's where things get a bit more complicated than before, because previously we assumed that all the velocities were the same. But we can't really assume that anymore here, because in this particular scenario, we didn't say the velocities are the same. We told you that the voltage was the same. Now, what will the voltage do? Well, the voltage, as we said, is going to give an electric field, which will accelerate this. But basically, because we've done calculation on this before, basically we need to think of the voltage as supplying work to this particle. And this work will then give you the kinetic energy. So we need to think of it as work, which is equal to QV, will give you KE, which is half mv squared. Now, the charges are not necessarily the same, depending on which particle you're talking about. The voltage is, so the kinetic energy might not be the same, and the masses are certainly different. And then you need to work out the corresponding velocity. So we'll start with the proton first. Okay. So for the proton, we know that the work is equal to the charge. We'll just say E times the voltage. We'll call V, capital V for voltage. And that equals half mpv squared. So that means V squared equals 2 times E times V. All right, 2eV over the mass of the proton, or V must equal the square root of 2eV over the mass of the proton. Well, with that in mind, we can get the radius of the proton. And that would be mass of the proton times the velocity of the proton divided by the charge of the proton, which is E, while we're at it, times B. And then you can really just cancel out the MP with the root MP. So you have root MP at the top, root 2 at the top, root V at the top. The E and E will cancel out. Basically, we'll get something that looks like this. Root 2 MP times V all over square root of E times B. All right. That's basically the idea. All right. So now that we've been able to get the radius of the proton in terms of your constants, we just need to really repeat this sort of same process with your other ones. So you've got a deuteron, which is 2 mass and E. So then, of course, W equals QV equals half mv squared. So we know that EV, in other words, it has the same work applied to it because it's a supplied to, it has the same charge, but its mass is actually double. So it will affect its velocity. So this is actually just going to be mpv squared. So that means your v squared will equal EV over MP, where V must equal square root of EV over square root of MP. Now we know that the radius equals mv over qb. Now in this case, that's 2 times the mass of the proton times the velocity, which is root E times V, all over the square root of that, divided by Q, which is E, and divided by V. Of course, we can see that this cancels out. So you'll get, and of course, the E and E cancels a bit. So you get 2 square root MP times V all over EV. So this is the radius of the deuteron. So if we do a quick comparison with this one, you've got root E times B. This is E there should be a square root of E on top of that as well. So we can see that the radius of the proton, everything root MP root V, you've got a root 2. So you've got root that. So basically, this is equal to root 2 times root 2 MPV over root EV. And this was what we worked out to be the radius of the proton. So in other words, the deuteron radius will be 41% bigger. Okay. Now we can do the same thing with the alpha particle. So again, you've got W equals QV. Of course, with the alpha particle, we know that the mass is equal to 4m. And we know that Q equals 2e. So W equals QV, and that's equal to K, which is half mv squared. Now, that means, in this case, your Q is 2e times V. That's equal half times 4 mass times V squared, which of course is 2 mpv squared. You can see that V squared in this case will equal EV over MP, so that V must equal the square root of EV over MP. The radius must equal MV over QP, which is 4 MP times the square root of EV over MP, divided by 1 over 2e for the charge, times 1 over V. That gives us 4 and 2 cancel to give you 2. You will get 2 times square root MP square root V all over square root E times B, which is exactly the same as the radius of the deuteron, which of course is root 2 times the radius of the proton. So there we have it. We then can basically say that in this scenario, if you have a particular radius there, this will be root 2 times that radius. This will also be root 2 times that radius. And the reason why we can't just rely purely on mass to charge ratio as we have been before is because we no longer assume that the velocity is equal, but we actually have the voltage is equal. And because they have different masses and different charges, that would then result in different work done to the particle with a different charge. And with different mass, that's also going to mean a different idea of what happens to the velocity then, given that the mass is different. So the K will be affected. And that's basically how you do this.